Good afternoon. Welcome to our American audience and benvenuti a chi ci segue dall'Italia. I'm very excited to be hosting this event. This is the first symposium in a series of three symposia on a topic of science and technology. The next two symposia will be held on April 15 and May 19th, and they also will be virtual via Zoom like the present symposium. It's a great pleasure for me to host this symposium for various reasons. It was promoted by the Italian consulate in Philadelphia and the Italian government, which we greatly thank for their support. It was organized by a prestigious Italian-American nonprofit organization called Filitalia International, an organization founded in 1987 to promote and preserve the Italian culture, heritage, language, and customs throughout the world. And finally, this symposium is about green plastics or sustainable plastics, a topic of current and great interest worldwide. It has been a privilege for this symposium to have our speakers today. They are experts in plastics, and together they bring more than 60 years of valuable experience from different areas: academia, education, industry, and research. And therefore, they offer a comprehensive and current perspective on this topic. I also like to praise the speakers for their effort to make their presentation accessible to a general audience without knowledge of chemistry and material science. I like to stress that, as you will hear, the biography of today's speakers proves that Italy can retain and export their own experts, as in the case of Professor Abate and Professor Celli, but Italy can also attract experts from other countries, as in the case of Dr. Bayer. Finally, many thanks to the fantastic team of Hyper Design, the firm that has done a great job in taking care of this symposium regarding the technology part and social media aspects. All right, let me introduce the first speaker, Professor Agnese Abate. Professor Abate is professor of advanced placement chemistry and science at the Malvern Preparatory School, coordinator of Science National Honors Society, and has several years of experience in science research. Dr. Abate also serves as assistant professor at Temple University, where she conducts research in the field of medicinal chemistry. She earned her PhD in chemistry in 2006 from Politecnico of Milan, Italy. Dr. Abate also worked for many years in the field of fragrances, use of polymers in organic synthesis, and direct application in products. Dr. Abate, please.
Right, I'm ready to share my presentation. Can you see my presentation?
Yes. We've lost, you stopped sharing your own video if you want to share your own video as well.
I don't know how to do that.
In the lower left of Zoom should be a button that says Start Video.
Yeah, I see that. Okay, am I good?
It looks like it's connecting.
All right.
I see you as gray, but that's okay if you want to just do.
Okay, all right, I'm gonna start. So I want to thank the Italian Consulate of Philadelphia and Filitalia International for this opportunity. My presentation is about introduction to plastics. So when I was a kid, one of my favorite movies was Charlie and the Chocolate Factory. And my favorite Willy Wonka creations was the Everlasting Gosstopper. And that's a special chewing gum of 3 courses meal, tomato soup, roast beef, and blueberry pie, and in one single gum. So that's something that you can find these days commercially available, like flavor changing gum. But in general, chewing gum is a polymer, and its main component is a gum base. And the actual composition of a gum base is usually a trade secret. However, we know that chewing gum is mainly based of 60% polymer, which is usually gum arabic or natural rubber, and or synthetic, it can be polyisoprene. And the 40% is made of flavors, sugar, which is the main component, and the colors and the wax. So the gum base is soft, non-digestible, water insoluble, and which means that you can chew it, and never breaks down. And it's designed to be chewed without being swallowed, obviously. To get any sort of flavors, we these days we use the process which is called microencapsulation, which is basically that is a process where the liquid flavor is coated inside microcapsules, and the coat is made of proteins or simple wax. And when we chew the gum, the flavor is released in the mouth. But what are polymers? The IUPAC defines polymers as micromolecules. For micromolecules, we define big molecules, like the molecule you have here on your left is the DNA that is in our body. The DNA is a micromolecule because it's very big and is made of many atoms. And in general, polymers are substances made of long chains of repeated units, and the repeated units is called monomer. From Greek, it means one part. And natural polymers are existing nature, and those are DNA, silk, air, starch, cellulose, sugar, proteins, enzymes, cotton. Those are all natural polymers. And natural polymers are produced by living organisms, and we as man, we learn how to copy the nature and reproduce synthetic polymers. And the long chain of macromolecules are usually made of covalent bonds, very strong bonds in between the atoms. And as you see here in the DNA on your left, the purple side, which are the connected bonds in between the 2 strands of the DNA chains, those are intermolecular forces, and the intramolecular forces are much weaker than covalent bonds. What kind of intramolecular forces exist? Those are there are 3 kinds, and the strongest one is the hydrogen bonds. We're probably familiar we're probably familiar with the hydrogen bonds, because the hydrogen bonds holds up together the water molecules. And so the water boils under Celsius because there are 3 hydrogen bonds in each water molecule, which is pretty strong. Another kind of intramolecular force is called dipole-dipole interaction, and which is it exists in the polar molecule. What are polar molecules? Are just molecules where you have positive and negative charges, because the atoms are made in a way that they create these separational charges, and these positive and negative charges attract neighbor molecules, and neighbor molecules, and that creates a force. And a much weaker intramolecular force is what is called van der Waals forces. And those are also called London dispersion forces, are here on the bottom. And those exist in all molecules, even non-polar. And those exist because the electrons move around the atoms, and they create instantaneous type of moments. And these instantaneous type of moments can be transferred to neighbor molecules and neighbor molecules or atoms, and then that creates the kind of attraction. All right, so let's go back to our polymers. So most of the polymers are commercialized, are man-made, and are synthetic substances. So that means there are derivatives of petroleum, like oil, and a few are derivatives of plants. And so most of them are made of they have a general formula of carbon, hydrogen, and oxygen. And that little monomer is repeated N times. As you see here in the picture, the N represent what is called the degree of polymerization. And the degree of a polymerization referring to the average number of monomeric repeating units in the macromolecule. And for example, the high density polyethylene you have here on the left, the N is in a range from 10,000 to 100,000, and it makes the high density polyethylene very resistant, very hard. And so usually the HDPE is used in containers like milk jugs, rubbing alcohol bottles, vinegar bottles, all bottles they are very hard to touch, and they can resist to corrosive substances. It's so resistant it can resist even to bleach. And this is one of the property of the polyethylene. And so, as I said, the degree of polymerization, it gives us a key property in the polymers and determine the physical properties, the melting point, and other physical properties. And so another very important polymer that I want to point out is a polyvinyl chloride, which is PVC, and is composed by carbon, hydrogen, and chlorine. And as you see here, the monomer formula. And why is it so important is because it's a flame retardant material. So we use a polyvinyl chloride in clothes for kids, for example, or for firefighters. So the reason is in the chemical properties of the carbon chlorine bond, which is not easy to oxidize. Its combustion is an oxidation reaction. They don't burn easily. And other products made of PVC are toys, car supplies, clothes, and container packaging pipes. Pipes is also another one, very important. All right, so other polymers are in this picture here, these pictures. So you have high density polyethylene, which is used as chemical resistant objects, for example, cutting boards. PVC, I just mentioned, is used in pipes. mostly, and is resistant to acids and bases, so corrosive substances. PET, polyethylene, is used for plastic bottles and is more flexible. And PS is a polystyrene, is used as is a common foam, and is impact resistant, is perfect to pack glass bottles and delicate materials. And the PU is a polyurethane and is used as insulator. It comes in as a spray, like a liquid. When you spray, it solidifies and releases water. When the water evaporates, it looks like the foam that we are familiar with. And the PC is a polycarbonate, which is used in constructions. It is very stiff and hard. And the other polymers are here, and because the polymers' physical properties depends on the chemical structures. So I don't want to show you the chemical structures, it's useless, but I want to talk about these type of physical properties. For example, rubber here on your top left, polypropylene is an example of elastomer. Where the polymer has the ability to return to the original state when it's stretched and deformed. And polyacrylate is used here on the bottom left. Is used in for synthetic fibers and wool, for example. And as you see, the chemical formula is very similar to the rubber, but it has oxygen. So that changes the structure, and that changes also the physical properties of that. Another kind of polymer is the foam that you have here on the bottom. And the foam is a polystyrene. And I show you here the chemical structure because I want you to notice that the polystyrene is made of these big, the monomer is made with this ring. And this hexagon, which is called benzene, occupies space in, so as you see here on your bottom right, you see the space that occupies each of these rings in a chain. As you see, there is some space in between these rings. So this space allows the foam to be soft and more compressible, as you can imagine. And another kind of polymer is a composite. A composite are polymers consisting of fibrous reinforcing materials, are made of physically combining two or more materials layers, and they are usually used in fiberglass, electric sensors. All right, and other polymers are here. I have here on the left, I have a thermoplastic, which is very important. It's one of the few recyclable polymers that I'm mentioning here. And for example, an example of these is the Lego, but there are so many, even toys for kids are made of this kind of plastic. And here you see the monomer is not just one monomer, but is made of three different units. And so it's more complex than a single monomer. And so the resulting physical properties is very hard to touch, but it can be, you can add colors to it. So because of the double bond present. And so I think this is very common polymer. So I want to mention this. And here on the top right, you have a gel, which is a gel polymer, which is something that you're probably familiar with because you probably see in, for example, meat packages, when you have the absorbent layer on the bottom of the meat or the fish contains this kind of gel. And this gel is a super absorbent for liquids and is made of a polymer plus liquid electrolytes. And you have here the formula, you have salts, so they are able to dissolve in water and trap the water inside. All right, I think those are kind of polymers. Now let's talk about how do we make polymers. I want to present two kinds of reactions. The first one is the condensation. The condensation reactions is a formation of a covalent bond between two monomers. And usually when the bond is formed, water is released. This is an example of nylon. There are many kinds of nylons, but in general, nylon is made by condensation reactions. And usually this reaction is pretty clean. There are not byproducts, and usually, except the water that is released, there are not any main byproducts. And another kind of reaction is the addition reaction, which is also called chain growth polymerization. And it starts with a radical. So usually it's possible when you have a double bond like this in a styrene, for example. And so the polymerization reaction is very useful because it can be done these days with under control conditions. But this process now will always be like easy like that. The control addition reaction is being invented by Ziegler in Germany and Natta in Italy. Two scientists who independently discover the way to make this reaction under control. So to control the products and avoid amorphous products. So before them, the process of polymerization reaction was completely useless and without control. So as I was a student, as a PhD student at the Politecnico of Milan in Italy, and I visited the Natta lab. Natta studied and invented his catalyst at the Politecnico of Milan. And I visited his lab. It was a sanctuary. And where Natta invented his polymerization process, he had like 20 students with them. And it worked basically at the same time as Ziegler, the same exact time, to find out the best catalyst to control the polymerization reaction. So they basically screened all the metals in the periodic table, and they found out the transition metals, and they found out the best, what is called these days the Ziegler-Natta catalyst. And so after their discovery, they were both awarded with a Nobel Prize in Chemistry in 1963. All right, so the modern polymerization process these days is made in aqueous solution, so in water. So basically, so a free radical initiator is added to a water-based emulsion along with soap-like materials known as surfactants. The surfactant molecules are they are made of both the hydrophilic and hydrophobic ends, so like a soap micelles, basically, and they form a stabilizing emulsion before the polymerization starts. So when the polymerization occurs, when so the initiator migrates, occurs when the initiator migrates into micelles, inducing the monomer molecules to grow and form large molecules called latex particles. Now, I want to clarify the difference between the plastics and polymers. So plastic means capable of change, but what is the difference between the plastics and polymers? Basically, plastics are constituted of polymers and plus other ingredients, and the other ingredients can vary based on the combination on the desired properties of the plastic we want to obtain. So there are many types of additive that we add to polymers in order to have different characteristics in a resulting material, like aesthetic, physical, mechanical, thermal, optical, electrical properties. And these additives are there are many around, and are usually they can be antioxidants, pigments like color, stabilizers. They stabilize the plastic from heat, light, oxidation, lubricants, and anti-static agent. All right, I think I'm going to stop here. Thank you for your attention. If you have any question you don't want to ask here, you can email me, and thank you again.
Okay, so for questions, there's a Q&A button at everybody for the attendees. You can type your questions into there, and Antonio will take a look at them.
Yeah, thank you, Dr. Abate, for your introduction on polymers and plastics. I appreciate your examples of everyday plastics we encounter in our life. And in the meantime, actually, I have a question for you. What polymers did you work in did you work with in your career? What are the ones you worked the most?
So I used to work a lot with flavors and fragrances, but at that time I worked with also gum base, which was my the gum base with chewing gum. That's why I mentioned that. And also worked with in the chemical synthesis, you can anchor a catalyst on a polymer. So I use polyethylene in that case, and then I use that catalyst to make a chemical reaction. And I think that's what I used. Was interesting.
Thank you. So fragrances means perfumes, colognes, basically, or?
Oh yeah, fragrances are small molecules that they're usually smelly, like they smells good, and they are produced to enhance special sensations. Like there are so many kinds, but flavors are different, so you usually eat them. But they have common chemical structures.
Were you allowed to bring some fragrances home, free samples home for you, or not?
Oh yeah, I did a lot. Yeah.
Is there any other question from the audience? Benny?
I do not see any in the Q&A.
Okay.
If that's confusing to the attendees, you guys can put them in the chat.
Okay. Yeah, I checked the chat. I don't. Okay, let me see Q&A. Okay. No, at the moment I don't have questions yet. So, okay. Professor Abate, thank you again for your presentation, for your time today. And I'm switching to the second speaker, Professor Anna Maria Celli. And Professor Celli holds a PhD in materials engineering from the University of Bologna, which I like to stress, it is the oldest university of Italy, founded in 1088. I repeat, 1088. So Professor Celli, so it's about 1000 years, Professor Celli works in the field of synthesis and characterization of biopolymers, mainly derived from biomass through the exploitation of agro-industry byproducts and agro-food waste, and in the development of strategies for a sustainable end of life of plastics. So with Professor Celli, we switch now from polymers and plastics in general to plastics derived from plants, from biomasses, from food waste, from agricultural waste. And in fact, in her presentation, Professor Celli will give us an overview of the characteristics, management, and research trends of sustainable plastic. Please, Professor Celli, go ahead.
Yes, thank you very much. I try to share my screen. Okay. Can you properly see the screen? See the
Yep.
screen?
Looks great.
Okay. Perfect. So I can begin my presentation. I would like, first of all, to thank the Italian Consulate of Philadelphia, Filitalia International, and organizer for inviting me for this interesting occasion. And I would like to show you, to begin to speak about sustainable plastics. So it's clear that plastics today are everywhere around us. It's difficult to imagine a world without plastics. And in about 100 years of history, plastics were able to substitute other materials such as glasses and metals, thanks to very interesting properties such as lightness, low cost, processability, and so on. And I remember you that plastics are produced starting from small molecules called monomers. These monomers have a specific chemical characteristic, can be linked all together by a reaction called, in general, polymerization, and it's possible to obtain very large molecules called macromolecules or polymers. And then it's interesting to see that the word plastics collects a very large number of materials with specific properties and functionalities, depending on numerous variables, such as, for example, the nature, the type of the monomers, the chemical structure of the chain, the length of the chain, the arrangement of the chain, for example, in ordered or disordered phases, or the possibility to create a network, for example, a bidimensional network. So we have a very large kinds of different materials. But in terms of bioplastics, we have to underline that we can speak about bio-based materials. Sorry, bio-based materials means that the materials derived from monomers that have a biological origin, or in general, the polymer has a biological origin. This means that the material derived from renewable resources. And this is different from the traditional plastics, polymers that we have seen, that derive from fossil oil, so from not renewable resources. So this is a first classification of bioplastics. This classification identifies a bioplastic according to the resource from which it derives. Moreover, a bioplastic can be also or biodegradable. Biodegradable means that the polymer can be cut by microorganisms such as bacteria or fungi. And the polymer can be converted in substances such as water, carbon dioxide, or also compost. Compost is a specific material that is that derive from the conversion of bioplastic in industrial compost plant. And the compost is a plant fertilizer. So in this case, we identify bioplastic according to the end of life. So a bioplastic can be bio-based or biodegradable or both, bio-based and biodegradable. Here in this slide, we can see some the example of bioplastics. First of all, I would like to underline that the global bioplastic market is very small, about 1–2% of the whole plastic market. So the plastic market is dominated by plastic that derive from petrol. But in terms of bioplastics, we can identify two big families. Indeed, in the left part of the figure, we can see traditional polymers, such as, for example, PET, polyethylene terephthalate. PET is the polymer of the bottles. PET generally is obtained from petrol, but recently some processes to obtain PET from biomass have been developed. For this reason, this PET is a bio-based materials. All these materials in the left part of the figure are so bio-based but non-biodegradable. In the right part of the figure, it's possible to see instead other materials. These materials are biodegradable and in general, they are bio-based. So we can see some specific characteristics of some of these bioplastics. For example, there are starch-based polymers. Starch-based polymers are polymers derived containing starch, cellulose, vegetable oils, and other components, natural components. So these materials are sustainable, 100% bio-based, biodegradable in soil and in marine water, and also compostable, so they can produce compost in industrial plant. These materials, starch-based polymers, are produced in Italy by a company, Novamont, and in Italy are called Mater B. They are very common in Italy. Other interesting polymer is the polylactic acid. Polylactic acid derived from sugar by fermentation is a transparent and rigid material. So, for example, it's used to prepare, to obtain a bottle, but also other rigid containers. It's also used, for example, for a 3D printer, and is 100% bio-based and compostable, but, for example, not biodegradable in soil and marine water. Other polymers are, for example, PBAT. In this case, the chemical formula is enough complicated, and this material is only partially bio-based because some part of these molecules can be obtained by starting from petrol. This material is interesting, very interesting. It has tunable properties, can be used to produce different products, and is compostable. These are three very common bioplastics in Italy and in Europe. But I would like also to show you another family of biopolymers. They are called the polyhydroxyalkanoate. They are emerging polymers, very interesting because they derive from bacteria. In the figure, for example, we can see the bacteria containing white granules. These granules are polymers. The polymers can be extracted, and it is characterized by properties similar to the properties of traditional synthetic thermoplastics. And this material is 100% bio-based, biodegradable in soil and in marine water, compostable, biocompatible. So it's really very interesting, but is characterized by very high cost. So after this example of bioplastics, I would like to show you some example of research trends. And I would like to start focusing on feedstocks. We know that now there is the need to substitute petrol, fossil oil, because the use of fossil oil has some issues, environmental problems, is not a renewable resources. So it's necessary to find other sources. And it's interesting to observe that in Europe, but in all the world, I think, there are the production of a very large amount of vegetable waste and food waste. So the idea now is to try to substitute this vegetable waste and food waste to produce bioplastic, to substitute fossil oil. This is a very important thing because for us, we can think waste as a resource of building blocks, monomers, fillers, additives, bioplastics, with enhanced functionalities sometimes. And so bio-waste is a source of new materials. This concept is in perfect agreement with the concept of circular bioeconomy. And European community is really very interested in these issues. And so European community funded a lot of projects that aim to exploit agro-waste for producing new materials. For example, the University of Bologna is involved in 3 interesting projects, prolific, know-how. Know-how means no agro-waste, and Agrimax. Here in this slide, there is the strategy that we are developing inside this project. We have a lot of agro-waste, agro-industrial residues, and food waste. For example, we are working with peas, green beans, chickpeas waste. We are working with wine pomace and wine shoots, in general with fruit and vegetable waste, or we are working also starting from agro-industrial residues, for example, residues from wheat bran, from Barilla, or residues from coffee, from Il Caffè. So it's possible to consider this waste as a source of new molecules. So it's possible to develop some extraction procedures to extract, for example, molecules such as polyphenols, cellulose, fibers, amino acid, pectins, sugar, starch, and so on. A lot of molecules and polymers. These molecules can become, for example, monomers, additive, fillers for new bio-based plastics that can be used in agriculture, for example, for mulch films or in packaging. A second strategy can be to start from the agro-waste and to develop biotechnological processes to valorize this agro-waste and in order to obtain monomers and polymers. I would like to show you some example of activities in these fields. For example, we can start from coffee residues and wine foams. Coffee residues and wine foams contain a very interesting family of molecules, polyphenols. Polyphenols have a very complex molecular structure, but are characterized by antioxidant and antibacterial properties. For this reason, they can use for exploit these properties, in order to exploit these properties. For example, we can mix the polyphenols in a polymer and, for example, polylactic acid, or we have coated the polyphenols on a polylactic film. In both cases, we have obtained materials that are antibacterial and cause the full immortality of some bacteria such as Staphylococcus aureus and Salmonella. This is very interesting for packaging application. Indeed, we tried to use these materials for pack food, for example, chicken in a vacuum condition. So we have used two different pack without antibacterial, so a normal pack, and a pack coated with polyphenols, so a packaging with antibacterial properties. And we have measured the bacteria that develop inside the packaging as a function of time. In general, in the curve blue, we can see that the number of bacteria increase as a function of days, and in about 11 days, the number of bacteria reach a limited number that cause the spoilage of the food. This occurs at about after 11 days. But if we use our new antibacterial packaging, the spoilage occurs 2-3 days later. So we have contributed to extend the shelf life of fresh meats. And this is a very interesting result that can be applied for this new kind of active packaging that not only contain the food, but also protect the food. So this is very interesting because to produce this packaging, we use polyphenols obtained from food residues, food waste. Other example, there are wastes that contain fibers and lignocellulosic compound, for example, wine shoot, but also grape pomace, potato waste after extraction, for example, of starch, and so on. A lot of waste contain fibers and the lignocellulosic compound. So we can dry and reduce directly this waste in powder, and we can mix this powder with a biopolymer, for example, a polydroxyalkanoate. Then we can use these new materials to obtain a packaging. The mechanical properties improved thanks to the fibers and the lignocellulosic compound. And we have obtained a composite that contains, for example, 30% in weight of fillers. This is a strategy to increase the cost of the biopolymer because the fillers doesn't cost too much, it's a waste. And all these results occurs with an eco-friendly process, without solvent, without other additives. So also in this case, there is a good opportunity to develop this new composite. Other example, in this case, we work with the wheat bran from Barilla. Barilla start from wheat bran to obtain its product, but a lot of residues are also produced. And these residues contain a lot of interesting molecules. We have extracted from wheat bran residues a specific molecule. So this is ferulic acid. Ferulic acid can be a monomer that, thanks a polymerization reaction, can provide new polymers, and these new polymers can be used for application in agriculture, but also in packaging. So we can prepare a new sustainable packaging for Barilla products starting from the residues of the Barilla process. Moreover, using also this directly, these solid residues, we can prepare biocomposite as observed in the previous slide. And also this biocomposite can provide packaging for the Barilla product. So we have a new 500% sustainable packaging for the Barilla products. These are, in my opinion, very interesting example of the valorization of residues, food waste, agro-industrial waste, to produce new polymers and new packaging. But we work also in the field of the end of life of plastics. In this case, the option of end of life for plastics are in general recycling, energy recovery, and landfill. Recycling is really very important because the material is used again, reused, is recovered. And here in this figure, we have for the different countries in Europe, the importance of the three ways of end of life of plastics. We can see that in some countries, landfill represent a very small percentage of end of life of plastics, and this is due to restriction of landfill. In Italy, the situation is here. We need to improve recycling. But in some cases, recycling is difficult. I would like to show you an example. There are some packaging that is multi-layers. This means that the pack is formed by different layers that are connected with the adhesives. These materials, this packaging cannot be recycled because the layers are made by different materials, so it's impossible to recycle this kind of packaging. But in other European project, Terminus, we are developing a strategy. We want to use an adhesive made by a biopolymer, made by a biodegradable polymer. So we have studied these materials, this adhesive, and we have selected enzymes able to degrade this adhesive. We have inserted this enzyme into the adhesive in a specific way that the enzymes are not active. Then we have built the multi-layer structure. So first layer, adhesive, and second layer. The adhesive contain not active enzyme. This is our multi-layer structure that can be used as a packaging for specific food. At the end of the life of this packaging, we can degrade the adhesive thanks to a specific mechanism, for example, with the water or UV irradiation. The adhesive is the enzyme become active, the adhesive is degraded, and we can separate the different layers. So we can separate and recycle the layer. This is really a very impressive strategy, a very difficult strategy, but there is a concept very important. When we prepare a new packaging, we have to design the packaging in a way that we know a priori the end of life of the material. This means we have to eco-design our product. This is a very interesting new concept for the plastic world. So, as a conclusion, bioplastics are a family of materials with different properties and applications, but they represent only a small percentage of the plastic used annually. Novel routes to produce bioplastic from wastes are under study in order to obtain also more sophisticated biopolymers application products. And also I would like to underline that today is very important also to eco-design product with a specific end of life in order to solve some problem related to the end of life of the material. So I have finished, and I thank you very much, all of you, for your attention.
Professor Celli, thank you very much. It seems to me, it sounds to me that your work has a double benefit, because on one end you reduce the waste, food, industrial and agricultural waste, and on the other hand you turn this waste into plastics. And the other benefit is that using this waste, you do not use non-renewable resources such as crude oil and gas. So I have there are two questions from the audience for you. So I'll go with the first. Why do most bioplastics require a commercial high temperature composting process to decompose? In other words, why they do not decompose in normal low temperature compost piles?
Only some bioplastics. For example, polylactic acid decompose only at 60 degrees temperature. And this is due to the chemical structure of the molecules, macromolecules, and the kind of enzymes able to degrade the polymers. So polylactic acid degrade only at high temperature. Other polymers degrade at room temperature. The process of degradation are really very, very complex, and is necessary also to try to improve the degradability of the bioplastics. For example, I know that a problem of the compost plant is that sometimes bioplastics degrade at a very slow rate. And so is necessary to improve this rate, for example, by using some pretreatment with enzymes or some mechanical, for example, reduction of the size of the product and so on. We are working with some composting plant to solve this problem. And it should be very interesting also to make polymers compostable at home, because not in Italy, but in Europe, I know that the home composting is important. In Italy, not so much, but some bioplastics are not able to degrade in home composting conditions. So the degradation, the capability of the bioplastic to be decomposed must be improved and studied a lot. This is one of the big problems that concern the world of bioplastics, but there are also other problems.
Thank you. Thank you. And the second question is the classification of bioplastics and the classification of bioplastic and recycled plastic involve the compost process? I'm not sure I understood the question, but so it's about classification of bioplastics and their recycling. Their recycling that is related to the compost process.
I can tell you one of my idea. Bioplastics are interesting because if they derive from biomass, so if they are bio-based, specifically if they derive from agro waste, organic waste. But when we consider the end of life of bioplastics, we have some different options. One option is the degradation in a compost plant. In this case, we destruct all the material, the link between the monomers. We destruct these bonds, and we convert the materials in water, CO2, and compost. It's important because compost is used in plant and in plant grow and so on. But in my opinion, it should be very interesting to preserve the bond that are present in macromolecules, and could be very interesting to recycle the bioplastics. This is a challenge because it's difficult, very difficult, because, for example, often the bioplastic are not suitable for recycling, but the recycling conserve the bonds that we have created using energy, and we can use again the plastics. So now we are studying also this issue to try to recycle biodegradable plastics. I don't know if I have correctly answered to the question, but I think that this could be an interesting option.
Now I have another question. What is the cost comparison between bioplastics and fossil-based plastics in general? I mean, is one class more expensive than the other?
Bioplastics are really very costly with respect to the synthetic plastic. I can do an example. Polypropylene, that is a very common plastics, cost about, I don't know exactly, 1-2 euros per kilo. Polyhydroxyalkanoates cost about 7-8 euros per kilo. So there is a very big difference. Another challenge is to try to decrease the cost of the bioplastics. For example, by increases the amount of fillers at low cost inside the bioplastics, or to obtain, for example, polyhydroxyalkanoate, controlling the diet of the microorganism, and specifically use organic waste as a diet for a microorganism that produce polyhydroxyalkanoate. In this case, the price can decrease at about 3-4 euros per kilo, but the difference is big for the moment.
Professor Celli, thank you very much.
Thank you.
Was very informative, and I would say your presentation seems to point out that there are good options. We are working on good options for the future, right? To protect the environment. So now I switch to the third speaker, Dr. Ilker Bayer, and he is a staff scientist at the Istituto Italiano di Tecnologia in Genoa, Italy, so the Italian Institute of Technology. Dr. Bayer has been working at the current organization since 2010. He received his PhD in surface engineering from the Department of Mechanical Engineering at the University of Illinois in the United States in 2006. He's also a visiting professor at the Department of Mechanical and Aerospace Engineering of the University of Virginia. His research efforts are primarily focused on functional coatings, hybrid nanomaterials, and the development of bio-based polymer composites for various engineering applications. So in brief, his area of work is applied and industrial research. He's also an inventor and holds an impressive number of about 30 patents between granted and pending patents. His presentation today will be about let me see, sorry.
I can say that if you like.
Yes.
Sustainable alternatives to plastics, history of bioplastics and future prospects.
Yes.
Kind of like a industrial continuation of the previous talk.
Yes.
Industrial point of view, let's say.
Yes. Thank you for saving me. And
no problem. No problem. I also forgot if I don't look at it. So let me try to share my screen. Does it look okay to everybody?
Yep, looks good.
Okay, so I think I'm going to repeat like most of the things that Professor Celli mentioned, but I'm going to look at it probably from a little bit industrial point of view and how I ended up working in this area. So actually, I grew up by the seaside. I mean, I spent most of my life by the seaside, and when I was in Illinois, also when I ended up in Chicago, I also spent more than 10 years by the lakefront. So whenever I used to see some kind of dirt or contamination or waste in the sea, I used to get so mad. But at that time, I never had any idea of realizing that we actually right now today we have a huge amount of plastic waste that is swimming in our oceans. Actually, I think that's called the plastic gyre. And then they say about the size of the European continent now we can find in the oceans plastic waste. And what's happening is this: they don't stay like in their structure, like as a bottle or as a container, and they start to get into smaller and smaller and smaller particles. They break down. They break down in size. They don't break down chemically, like we were discussing before in the previous talks. So they still maintain their plastic or polymeric state. So what happens is they go smaller and smaller in size as they break down in size. If it is PET, it is a PET polymer, which is, or PET plastic, which is in 5 microns. So what happens is the animals, the sea animals, even micro animals in the sea, they start to consider or think that these are food, and they start to eat them, and then it creates a big problem. So when I realized that, I said, okay, we have a couple of options. Either we recycle, as we saw in the previous talk. If the country we live in is very stringent on forcing all of us not to throw away our plastics, but to recycle them, I think that's okay for me, personally speaking. I mean, I am not a huge fan of bioplastics. So bioplastics, I think we need them. But if we can also properly manage what we are using right now, which is mostly petroleum-based materials, let's get them recycled, to instead of 5%, to 99% if we can. Or we can turn them into some kind of fuel. We burn them in an efficient way without polluting the atmosphere. and we can use them as fuel. But again, this is something that is still not there. So they end up somewhere either in the sea or in the soil or somewhere that we can't even imagine, that is basically right now eating away the environment, the ecosystem. So here I try to show you guys that sometimes, to me, when you throw away your cigarette, I was thinking, okay, cigarette is made of a plant, and then the rest is covered with a piece of paper. So if I throw it away, I don't care too much, even though it is kind of nuisance. Then when you see a lot of cigarette butts thrown out, and I thought, okay, they can still degrade. But then if you look at some numbers on the left, some of these things that we believe, even a toilet paper could probably take some time to degrade, especially in the oceans, because I am personally sensitive to the situation in the seas. So imagine if a simple piece of cellulose that we use, or cardboard, takes some months to go away. And then if you imagine that, as Professor Celli was mentioning, if that cardboard has some other foreign ingredients in them, some kind of plasticizers, some kind of pigments, some kind of additives, dyes, etc. So that cardboard will degrade probably in 2 months. You won't have any problem. But then if something else that is released from that stuff that is going to be toxic to the environment, to the living animals, or to even us, because we end up eating the fish and other stuff. So it is still a huge concern. So not only the time of the plastic that's going away, you should also think about this aspect, from this angle. Okay, I have a toilet paper, but if my toilet paper has a lot of painting, etc., features on it, dyes, etc., so that's going to probably create an issue for the environment. Of course, when the quantities, if you talk about tons of materials, right? So a lot of people try to attract attention to this, and they kind of end up, collecting all these plastics from the sea, and then they try to recycle them into even some kind of form of art. I also did that in South Italy some years ago. We were collecting plastic from the sea, and we ended up constructing a Christmas tree just before Christmas. So we thought, okay, we cannot recycle it, so let's make something useful out of it. But I just want to show you also here on the graph, here on the top, you don't have to look into this graph in detail, but what I'm trying to show you here is that there are a lot of scientific groups that are working on the degradation rates, or they are trying to measure for each and every kind of plastic that we use, how long does it take, like millimeter by millimeter or micron by micron, to degrade away, and then they kind of try to understand and correlate, depending on the type of the plastic, depending on the way it is prepared, is it multi-layer or single layer, etc. They kind of try to understand what is going on in terms of what they call degradation rate that you see here on the y-axis. So there are some really serious studies on these issues. So the picture on the left is kind of being quantified, being turned into just like the COVID, the virus infection rates. So the situation taking place live is being converted into some kind of statistics, so that you can understand also the significance of this problem in terms of scientific data or statistics. So I'm not going to repeat maybe some of the things that we were discussing before with Professor Celli, but you could be, one has to be a little bit careful. And there were also questions about that. So something can decompose, something can biodegrade. So what's the difference? So there are some differences chemically between something decomposing or something biodegrading. Most of the time, these two concepts are being kind of used interchangeably. So I mean, I'm assuming if you have something that is not biodegradable, but if it is decomposing into non-toxic building blocks or non-toxic monomeric structures or non-toxic elements, etc. For many people, for many environmentalists, also this is not a problem. So this is something that we should keep in mind. So what I'm trying to say that, for instance, if your polystyrene McDonald's French potatoes cup is able to decompose into something that can turn into non-toxic material in the soil, I think that is also pretty good. So, but that conditions do not exist everywhere. So, yeah, just a quick repetition of bioplastic. as we were discussing before, bioplastic is something that should basically turn into the environment as something that if it started from, let's say, a piece of cellulose, it should probably go back to cellulose. If it ended up starting from some kind of starch, it should go back to starch at the end of its life, or something similar. Or if it turns into a kind of fertilizer under the soil. Again, going back to this issue of industrial composting, especially something that you don't have to spend extra time, energy, and money to turn it back into these things, that is even much more attractive. And this is what we were just saying 10 minutes ago, that is called kind of the home compost. So when I throw the plastic in my trash bin, or in the soil, I just want it to become fertilizer, and that is, or turn into biomass. So that is I think the ideal case. However, the other problem is industry. So if you would like to make a drinking water bottle from a bioplastic, so what the industrialist people, what the plastics people ask you is that, okay, I want to have the same properties of the PET that I'm using. So give me a bioplastic that will have exactly the same properties of the PET. So they are really stringent on that. So sometimes you can achieve that by using, for instance, your polylactic acid polymer. You can try to duplicate the non-biodegrading material properties, but then this creates and gives you a little bit of a problem in terms of biodegradation. As one of the questions was talking about that. So maybe instead of just degrading it naturally under normal temperatures, normal conditions, you kind of did this kind of synthesize this polymer. So you probably need to kind of industrially compost it. So it's going to get more difficult because you need to probably increase the temperature, increase the humidity, or put some other extra enzymes that will eat away, or some microorganisms that's going to eat away this stuff. So it's a really complicated issue. But also keep in mind that you can make biodegradable plastics from petroleum, but you can also make non-biodegradable petroleum-based plastics from the natural resources. So for instance, there is polyethylene, exactly the same polyethylene that you would obtain from petroleum. You can also use corn, for instance, cornstarch or something similar to make the same polymer. So do you like it or you don't like it? It's again an issue of controversy, basically. So yeah, just like some examples. Of course, what I'm presenting here on the left is, I think if you look at these, most of the things you probably we should also consider them as food. And there is always food shortage in the world. So some people say, I don't want to use corn, I don't want to use starch, I don't want to use soybean, or I don't want to use an oil that is derived from vegetables, because I know that I can use it as food, or I can provide it as food. So, and I agree with those people. So that is why what Professor Celli was saying, of course, you can use these resources. They are renewable, of course. I mean, you can plant more and more corn, then you can grow it, you can use it, you can regrow it, assuming that the nature will collaborate with you. But it's a matter of balance between the food and the resource for the polymers. That's why I think use of these biomass residues or things that we throw away, I think would be the ideal thing. But again, there is an issue of logistics. So I also work with coffee waste, because in Italy, coffee, as you know, is something that's super used. So even collecting coffee waste is a huge problem. So it's very difficult logistically to get these things. And when you use biomass, unfortunately, is not something that is always the same material. So the starting material can vary. So if you take biomass from Brazil, if you take biomass from China, so there will be some issues related to the variations, because the soil is different, the conditions are different. So you might end up not getting repeatability in your material when you're constructing something out of that. So it's important also to keep this in mind. So sometimes that's why some bioplastic producers, they go back to the origin. They go back to the food, because the food is probably more reproducible. yeah, this is something that basically I just said it, so you just wanted to kind of highlight that. Your biodegradable plastics, bio-based plastics and biodegradable plastics, they are not the same thing. Just keep that in mind. As I said, you can make a non-biodegrading plastic from a bio-based, you can resource it from a bio-based, let's say, feedstock. I have been looking also at the, I have been also, because my former boss is now the minister in Italy. He's actually responsible for this kind of sustainability issues in Italy. So I am always trying to keep an eye on the news, etc., as to what's going on in Europe in general. So they say that, you know, some people believe that bioplastics will not resolve this issue of environmental pollution, particularly related to plastics. I think I kind of agree with that. So like I said, we have to balance very well. We have to encourage, or we have to fund people and research, industrial research and academic research that could probably find ways to recycle the normal plastics, but also we should probably look for some new pathways to make new bioplastics, but also maybe some kind of composites that you can use, for instance, a waste, a fiber that we cannot digest, that we cannot eat, coming from some food source, and then turn it into, or embed it into another biomaterial and create something stronger that is strong enough to, for instance, compete with something that is coming from a petroleum-based resource. Actually, when I was looking into that issue, I realized that actually bioplastics were made way back in history. As we were saying, that chewing gum, probably the natural rubber, that is this kind of resinous thing that kind of leaks out from trees in South Asia, probably also in South America. These are known as rubber or natural latex. And when you cross-link them, actually, you could probably, most of the car tires we use today actually originate from this. Now, the chemistry, advanced chemistry, now you can actually synthesize natural rubber, also the right structure of natural rubber, using more synthetic ways. But then imagine, people were using it thousands of years ago to waterproof, etc. Here, waterproof, I want to put a special emphasis on that. Please don't worry about reading the slide. I'm just going to run it through very fast. One of the issues with bioplastics are, when we were talking about that, also Agnese was mentioning the polypropylene, polyethylene, you can use them as a very safe containers because they do not absorb or uptake water. So you imagine a bioplastic bottle. I mean, in time, let's say that you filled it up with your fruit juice, and then after 5 hours, you come and you see the half of that fruit juice is gone, but you don't see it like spilled around. What's happening? That probably, if your material is not good enough, probably it's absorbing, or like a sponge eating up this liquid. So many bioplastics suffer from this. They do not have stability when the humidity conditions change. So they get rigid, they get plasticized, they uptake the water. And then, so these are really some issues that the bioplastic people should still address. So then, throughout early, let's say, or the mid 1800s, some work was going on in Europe, and then people were inventing some new plastics made from cellulose. They were changing the structure of the cellulose to make the cellophane, like the cigarette wrappers, transparent. So cellulose ended up going from a fibrillar state to a kind of amorphous state where it became transparent. So this thing became quite famous. Then we also talked about these polymers that you can extract from bacterial systems, that they are known as PHPs or PHAs, and I think they were coming way back in early 1900s. But right now, if you look at today, I think this bacteria fermentation. So basically, these are, imagine like a beer fermentation. So you need some technology. Like imagine you are producing huge amounts of beer. So you need some kind of technologies, industrial facilities to produce these kind of plastics in a controlled way. If you want to do this kind of fermentation-based synthesis of bioplastics. I talked about cellophane, and then I think early 2000s, some big companies, that were basically in the business for other things like Dow Chemicals, Cargill. There are other ones, local ones, like we mentioned before in Italy as well. They ended up getting into this business, and then they realized that actually that could be a huge market for bioplastics, even though I am talking about several drawbacks related to petroleum plastics. That could still be open, big open areas, especially if you consider the biomedical materials, because some of these things you can probably use in your bodies or use them as medicinal scaffold materials, or even in surgery you can use to replace bone fractures, etc. So there are other things. So most of these companies saw these and they said, okay, maybe we won't be able to address issues related to super stringent food packaging conditions, but maybe I can handle something about mulches for the agricultural, things, or I can make flower pots that when I bury under the soil, the flower pot will also, the plant is going to also eat up the flower pot as fertilizer. So it is still quite a good market. Another thing is that, for instance, I worked in the lab, I made some different types of celluloses, but then if you are using processes, let's imagine a small scale first before going up to large scale. If you are using processes that a common or a standard plastic manufacturer cannot adapt to, that is going to create you a huge problem. So if you want to make a startup or something, for instance, your process should be really, really adaptable to, let's say, a plastic company's process, in which, for instance, extrusion is commonly, melt compounding is used, extrusion is used. So if your bioplastic is a thermoplastic means that you can process your plastic by melting it, solidifying it, remelting it, resolidifying it, etc., just like the 3D printing. So if your bioplastic, let's say that you invented a bioplastic, if your bioplastic has this capability, then I think you're in good shape, and then you can go further in terms of scaling it up or offering your material to large-scale companies. So if it's a thermoset, like an epoxy, epoxies, that they start liquid and they become rigid, and usually recycling them is almost impossible because they set in a chemical structure that reversing it is really difficult. Also car tires, when natural rubber is cross-linked, so recycling it is again an issue. Although there are some now technologies that kind of figure this out, but it is something that is quite new. Also, recycling, I was defending recycling at the beginning of my talk, but recycling also, one has to be careful because every time you recycle a polymer, even a standard polymer, you kind of lose something. You lose, if that polymer was, let's say, had excellent mechanical properties, a balance between rigidity and flexibility, that some of those will be lost because each time you increase the temperature in a plastic system, you create this process known as oxidation. Again, this goes back to so you oxidize something at higher temperatures much easier. So when you go to high temperatures, things start to oxidize. So oxidation of a plastic means it is partial breakdown. So if you start losing the molecular weight that Agnieszka was mentioning before, if that molecular weight was 50,000, when you recycle it, probably after the second, third time, you probably end up having 30,000. So that molecular weight is not going to be the same. So it's going to reflect on your final product. This is even more difficult to address when you are working with bioplastics, because they will oxidize much faster, they will degrade much faster. So this is something that one has to be really careful. That is why sometimes you probably notice when they say on Coca-Cola bottles, this is 30% recycled PET. They realize that, okay, I cannot make this bottle from 100% PET because of some of the reasons that I just said. But then what they can do is, okay, I can use maybe part of that recycled back into my virgin, let's say, plastic. At least I can still contribute in terms of recycling. Yeah, the other thing that I want to say, it's something that I think none of us thought about before. Most of the plastics that we find around, Agnieszka mentioned that a little bit, but I think she didn't mention the plasticizers. Most of the time, you need to add something to your plastic because either it's too rigid or it's too soft or it's too hydrophilic, or it doesn't resist the UV sunlight, etc. So you end up getting these, putting these additives, and if these additives leach into the food, especially for food contact, you are in big trouble. You can be in really big trouble, and you won't be able to get FDA approval, etc. for your product. So if you are making a bioplastic and if you are still using a toxic plasticizer, for instance, then it really doesn't have any meaning when if you're gonna, especially if you're gonna go for the food industry or the packaging industry. So when you talk about let's say additives for plastics or plasticizers, you should also look always to the natural alternatives of these things also. Instead of using a standard toxic plasticizer, you need to go find a plasticizer that is probably coming from soybean oil or something similar, or even a coloring pigment. Might be probably has to be some kind of a natural colorant instead of a pigment that might have some issues for health. Yeah, this is again, as I said. So as you can see, most of these things, especially stretchable stuff that we usually use to cover our fruits, etc., even if you make it from bioplastics, and even if they meet the transparency requirements, etc., you still need to be very careful what you're putting inside of your materials. I'm going to say a couple of, probably this is like the last slide or so. I'm going to tell you guys a little bit about what we do. We have an industrial, let's say, a project right now where we use waste, let's say, used paper, recycled paper, and we put that recycled paper, a huge amount of this recycled paper, into bioplastics. As you probably will remember, that polylactic acid, for instance, has this problem of home composting. But then if you add a certain amount of, let's say, natural fibrous material in these things, up to 30%, even more, you can actually achieve even home compost kind of capabilities here. We started this project some years ago. Now it's almost getting commercialized. And then we could make, by simple, plastic processing techniques, we can transform. So we call it paper-based thermoplastics. So you basically take paper, you kind of process it, you turn it into some special format, and then you process it with a bioplastic. You can process it with any other polymer of your choice, but in this case, we also choose a bioplastic thermoplastic, and then we end up producing, for instance, cups for ice creams, or even spoons or coffee cups, etc. Yeah, this is something that's how it kind of started. So it is not too old, actually. It's a couple of years old, but we made quite a bit of advance in this area, especially now that basically, so looking at the trends, like I was saying, you need recycling of, in this case, paper, or in the previous cases, other biomass resources or your food, try to transform it into something useful. As I was saying earlier, the logistics of this thing is important. So if you can find a coffee bean, let's say skin waste, but then how are you going to collect them? Where are you going to collect them from? How are you going to put them together? Where are you going to store them? I mean, there's a whole bunch of issues there. The other thing that bioplastics are at the moment not sufficient is the transparency. So transparency is only maybe for one or two things biomaterials you can still do. So it is something that we still need to look into. Yes, biomass into bioplastics. The previous talk was very nice on this issue, but there are some issues how to sort out biomass. Is it homogeneous always, or what if I use biomass just for fertilizer? Economically, how can I, where can I, put the green light or the red light? So the other thing is you have to be really careful. Whatever you kind of invent or you patent, it has to be quite adaptable to the technology, production technologies out there, because even the big companies, they don't want to invest because they realize the investment could be huge in order to transform their product line from, let's say, polypropylene to something that you came up with, even though your material is almost like head-to-head to the polypropylene. This is, I think, the last one. So I know for a fact that, for instance, in Italy, right now, when you call these vending machines to take your coffee or beverage or whatever, so usually right now, all the cups and also all the stirrers, they have to be bio-based, they have to be non-toxic. So they are banning these things. And so the producers are a bit in kind of in a chaos right now. They are also worried. But we're going to offer some alternatives to them. Sometimes you can use a piece of wood, and you can think of that. Okay, I can just use a piece of wood, but then they say that they don't know that wood, where that wood is coming from. What was that wood properly conditioned for food contact? Because I'm inserting that stick of wood in my coffee, and I don't even know, how it was processed. So there are some issues. So I think it's a little bit of an issue of the governmental, let's say, legislations or stringent laws that every country or every, let's say, group of, let's say, in the case of European Union, a group of countries can figure it out. But from what I see looking at this slide, I think US is a bit behind, in the sense that I think US is not really imposing too much pressure on plastic manufacturers to transform at least some of these things into bio-based versions or biodegradable versions, or less, let's say, more environmentally friendly versions. But I see that even here in Italy, aside from the European Union regulations independently, there are some stringent, let's say, regulations coming up. At least they are trying that, so it is encouraging. Also in China, looks like they're also moving in the right direction. Yeah, I think that's all. I hope it wasn't too long and too boring. And again, thanks for the invitation to Antonio, and also to the consulate, Italian consulate in Philadelphia.
Dr. Rilker, thank you. Many thanks for your comprehensive and detailed presentation. We appreciated your, I would say, industrial, realistic, critical perspective on bio-based plastics, and your mentioning about practical aspects of bio-based or using bio-based plastics, such as, or I should say, diffusion development of bio-based plastics, such as logistic issues. So I have one question. One question for you, although the Professor Celli answered already, I think, to a similar question. But anyway, the question is, I'm hearing a lot of fascinating scientific ideas. However, I'm concerned that bioplastics, or even recycling of traditional plastics made from petroleum gas, petroleum/gas for that matter, will never be too important, since petroleum is cheap and it is cheap to waste it. Meaning it is cheap enough to waste it. Can you comment on the financial aspect?
Yeah, I think I said something about that. True. I mean, petroleum is still plentiful, much cheaper. In general, for instance, in the US, there are a couple of companies right now that are using carbon dioxide, because carbon dioxide is a greenhouse gas, right? And it's something that we are generating left and right. So you can actually also transform carbon dioxide into a bioplastic, biodegradable plastic. And this could be, this is going to probably in the next 10 years or so, you're going to hear about that. So this also could be really cheap. What I'm trying to say is that I agree with the question that right now, in terms of cost, logistics, as I was mentioning, that I can just make the plastic and throw it away, and because it's coming from oil, that's all right. But then remember that in the future, maybe not today, I consider carbon dioxide as waste, because we are generating this carbon dioxide. So we will find other resources that will be alternative to petroleum, but with the same competitiveness, in the sense that it is not going to be crazily expensive. It's going to be also something that we will not want to emit, let's say, into the environment. So at the moment, yes, the cost is an issue. The reproducibility is sometimes an issue, I must be honest. But regulations are not there in many countries. That's why oil-based oil is always a good, is a cheap and easy resource. But imagine also the history of the oil-based plastics. So it took a long time to transform oil into plastics. In certain cases, this was just an accidental discovery. These were accidental discoveries. So the same thing is happening now with some other resources, such as, like I was saying, carbon dioxide, or some of the maybe agricultural waste that will be so abundant that maybe throwing it away will be more expensive than transforming it into something. So I think it's going to take maybe a decade, maybe a little longer, but I'm still hopeful.
Thank you. So we are concluding our symposium. I have a few communications. So first, this symposium has been recorded and it will be posted on the symposium webpage and YouTube later. Secondly, there is a survey that will be available to the attendees. So if they stay tuned, the survey will open and they can answer a very few questions about the symposium, and their answers will help us to further improve on the next two symposia. I want to give many thanks to the speakers. They made this symposium successful. I also have many thanks for the attendees, and I hope that they will join us for the next two events, one on April 15 on innovation in aerospace, and the next on May 19 on 3D printing or additive manufacturing, and its fascinating applications such as in medicine. We'll have a guest from for the 3D printing symposium. We'll have a guest from Jefferson University talking about, again, applications of additive manufacturing in medicine. And for the symposium on April 15 on innovation in aerospace, we have we'll have 5 speakers from Italian, American, multinational, world leading companies, telling us what's going on in aerospace now and in the near future. I also want to thank very much Hyperdesign again for their outstanding work in ensuring a smooth connection. I thank lastly the Italian consulate in Philadelphia and Filitalia International. If I haven't missed anything, if I missed something, Benny and Eligio can intervene. But I think I said what everything I was supposed to say. And again, thank you very much to everybody who contributed to this event, the speakers, Hyperdesign, the attendees, and the Italian consulate, and the and Filitalia International. Thank you very much. I hope to see you on April 15 and May 19. Thank you very much.
Yes,
Thank
you. And the survey will open in your browsers automatically as you leave the webinar.
Thank you, Benny. Thank you.
Yep.
Thank you, everybody.
Thank you. Bye-bye.
You can now leave the.
Bye-bye.
Thank you.
Have a good
Bye,
one.
everybody.
Take care. Bye.